So good afternoon, everybody. Welcome to our afternoon session of today, Thursday in Hawks. Today I have the pleasure to introduce Rabah Abdul Khalek. He got his PhD at Nijmegen University in the Netherlands in September 2021 last year. And then he joined as a postdoc in the Theory Center here in JLab. And he works in perturbative aspects of QCD, in particular trying to do phenomenological determination of the hadronic structure of the hadronic structure with a strong focus using machine learning techniques and neural network. And actually that's what he's going to be talking in this set of 2 lectures. So the floor is yours, Rabah.
Thanks. Yeah, thanks Juan, thanks Caroline, thanks Alex, everyone who organized this call. Thanks a lot. I'm just going to say, as Juan said, like if you have a question, just raise a hand, interrupt me, and please be relaxed. There's not much slides. I think I will only introduce like 10 slides, then I'll be basically giving you a tutorial to play with. Also, no pressure on the tutorial, just do whatever you can in the time given, and it's just fun to, it will be fun to work with, so nothing too hideous. So the way I'll start is to give a recap on machine learning. You've already had 2 sessions, well, 2 different persons talking on machine learning, and I'll just scan it quickly. And then I'll focus on neural networks, which is the main algorithm that I worked with during my research. I'll give a broad introduction here, and then I'll move to a specific type of neural networks, feed-forward neural networks, which are probably the most easy to imagine and understand. Then I'll talk a bit about statistics, because it will be important for the tutorials. And generally, you can't separate statistics from machine learning. And finally, we will start playing with the tutorial. So the first slide I would like for you to just dive into is also a question we discussed yesterday. So when do you need machine learning? Let's say you have a problem and you're trying to incorporate machine learning to solve it. The first questions you're going to ask is my problem. So am I trying to find hidden patterns in my data and trying to find, classify my data into clusters without me knowing the classes of this data? Like I just have a bunch of data and I'm trying to, organize them. This question usually is related to or linked to unsupervised learning. So it's when you have a data where you don't have labels on and you try to cluster it based on patterns. And that's one class of machine learning techniques. Then you start asking, okay, what if I have labels? What if I want from my machine learning to give me a set of actions I do in a specific situation, or I want to extract a law from my data, something hidden in my data, but I know how to label my data, I know the uncertainty on my data, I know most of the things. Then you go into the field of supervised learning or reinforcement learning, right? And then you start asking, okay, so what if I want my algorithm to learn, to play a game like chess? So I wanted to learn from its mistakes and to progress by playing many, many times over and over without me giving any data. I would just give it people to work with or to play against, but not the data. And that's where you step into active learning. So the system will learn from itself. And if you're able to do that with a lot of data for it to improve and learn, then you can end up using reinforcement learning. And this is where you see a lot of example in real life where people created these chess machine learning algorithms that were able to beat the world masters of chess. But if you can't like train it on many instances and many data, well, machine learning won't be useful in that case. So this is an important here class that I try to always emphasize on, that sometimes you just should avoid using machine learning. It might not be useful. But anyway, so what if you have a data and you try to learn something from it? You have a set of limited data and you just try to extract information from it. This is passive learning. And so you ask yourself a question: do you have access to data that represents your whole problem? Like, you don't also need, you also, like, you need a lot of data to represent all the possible outcomes of something you're describing, not a specific set that is only like specific case to a specific situation. So if you do have a lot of data, then you can basically progress in this direction, and either you end up with, well, it depends on your problem, but so let's see. So could a knowledge human decide what action to take? So do you want to inject some information to your model, or the neural network should recognize how to deal with the patterns itself? And based on this question being yes or no, you end up either in machine learning not being useful, or you end up with a supervised learning, where you use all these neural networks, the regression techniques, etc. And this is where today I'll be focusing on supervised learning. So another overview. So we'll be focusing on supervised learning, and inside supervised learning, you can either end up classifying data or with labels, or doing a regression. So fitting a curve, you know, finding underlying law of some data. And today, yeah, I'll be talking about regressions, and mainly this specific branch, making predictions. You have, okay, I've talked about classification. When you move to unsupervised learning, you can use it, for example, to dimensionally reduce your problem. Sometimes you have a lot of inputs and you don't know which one to use to infer a specific model of information. So you try to reduce unneeded features. This you can achieve with unsupervised learning. You can also use clustering, as I said before. And finally, there is the branch of reinforcement learning, where you try to penalize the algorithm to learn from itself. So this is also another useful class. Okay, here we dive into neural networks. Okay, and this is well, it's claimed to be the most complete chart of neural networks, and I'm not going to go through them. And most of them I haven't worked with, but just to give you an idea on the large range of applications. So for example, today I'll be talking about feed-forward neural networks, which basically you give it an input and it propagates in one direction, and it gives you finally an output. So you can see it as a function of two inputs here. Usually, for example, in what we call feed-forward neural network, you have activation function, which I will also remind you of in the next slide, where are basically sigmoids or ReLU or hyperbolic tangents. While if you change the class of function you use for activation function, you end up with a completely different class of neural networks that is useful for other stuff. And once you start adding more layers, you have the deep feed-forward neural networks. So you have like, these are useful for big problems, classification problems, and very complex data patterns. Then you have, for example, the recurrent neural network, where basically you propagate into one cell, and then the cell takes the output as input again and propagates it to the output. So this is also useful. I mean, you know, for every problem, it seems there's a specific neural network that in the literature is optimized for something. LSTMs, for example, has the characteristic of memorizing what input went through a cell for a certain amount of time. And that's useful, for example, for text recognition or voice recognition, where you need a certain amount of information to be processed at once, not only one specific data. So you keep track of the memory. You have cells sometimes that have that include some noise on whatever passes through them. So for example, to avoid overfitting, one of the techniques is to introduce cells that just perturbate the input and allowing the neural network to explore something new without really being distant from the law, from the truth, etc., etc. So you have okay, we step into Boltzmann machines that have completely different functions. You have the convolutional neural networks and deep convolutional neural networks that are useful for image processing, that each layers of them can learn specific features of your image, etc., etc. So you see the range is large. I'll be talking mainly about feed-forward neural networks. And I put this slide because I just love this channel. I invite you all to look it up. It's on YouTube. And basically, this guy just do visualizations of neural nets like that and their mode of operations. So for example, if you're trying to recognize a picture where you draw a 2-digit by hand, this algorithm basically splits this picture into pixels, and it measures the level of grayness of each pixel and would eventually recognize the digit, basically. Okay, so let me introduce the feed-forward neural networks, their mode of operation, right? So let's take the most elementary minimal neural network. You have 3 inputs and just 1 neuron that propagates through it. The general way you would formulate a neural network is that this guy, this node, N1, would be equal to a certain function called activation function that takes as input the sum of these inputs multiplied by weights. So you can see them as these arrows here. So these weights multiplied by the inputs plus some bias, theta1, that you add linearly. And this is it. This is what neural networks are. So it's just a chain of these elementary nodes. Now, one of the most important things is the choice of this activation function, which depends also on your problem. So for example, I want to do a regression, right? I want to fit a curve that is continuous in some inputs, let's say X, Y, and Z. Mainly, you want to use a linear activation.
Excuse me.
Yeah, go ahead.
We have a raised hand by Matthew Ulion. Please go ahead.
Yeah. Hello. I have a question about the bias. You write as theta1, so it means you only have one bias for the whole neuron or for one input?
Yes, exactly. So every node has a bias associated with it.
Okay, so it's not the inputs which have the bias, it's the neuron itself.
Exactly. The bias is not associated with the inputs, with the internal node, if you want.
Okay. Thanks.
Thanks for the question. So yeah, depending on your problem, you would choose different.
Excuse me.
Oh, another. Yeah. Go ahead.
Derek, go ahead.
Hi, sorry, just a quick question. So what's the like when we write the theta bias, what does that bias mean, I guess, in terms of the system? Is that like trying to weight like this neuron might be activated more often than others, like based on how like what?
Yeah.
What does it mean? Sorry if that's a bad question.
No, it's a perfect question. Actually, it's a hard question. I mean, first you should see it as an extra degree of freedom, right? So it has a different function than the weights, which are multiplicative. This one is additive. So it creates an offset, if you want, from whatever if you need a linear offset, this bias basically provides it. which you can't achieve with the weights on their own. I hope that maybe clarifies it a bit.
Thank you.
So, for example, when we initialize the neural networks, usually we set this bias to 0, right? So, like the first instant the neural network sees the data, you can choose these biases to be across the neural network to be 0. But eventually, the neural network prefer to use these biases because it's just easier to train. You have extra degree of freedom, and usually it shifts from 0, so it helps the neural network to train.
Excuse me, Rabah, we have another question.
Yes, go ahead.
Rutika.
Yeah, so I mean, this just to clear the confusion, this θ1 as such has no relation with the input epsilon1, right? It's just how the neuron 1 gets linearly scaled. Like it's a degree of freedom just for the first neuron.
Exactly.
So θ1 is linked, right?
Exactly that, yes.
Okay, thank you.
Yeah, thank you. Other questions? That's great. Thanks for all the questions. Yeah. So based on the problem, you choose an activation function, and this would give you different outcome, right? So if you choose, for example, a linear function, activation function, this would allow you to fit a continuous function. For example, if you put it in the output layer. There are other functions like sigmoid or ReLU that have also sigmoid and hyperbolic tangent that are bounded between 0 and 1 or -1 and 1. And these are usually useful in the hidden layers where you try to basically keep your values or keep your parameters, the weights of the neural networks, not super crazy. So they're whatever you choose the weight, it should give you a value between -1 and 1, not something crazy. So usually these functions are used inside in the hidden layer. And also the choice of activation function depends on the efficiency of convergence. So you might find out that the sigmoid and ReLU give you similar results, accuracy, but you would choose ReLU because it's faster, for example. And usually it is. ReLU is created because it was faster, mainly for deep neural networks. Anyways, so this is a small cell, but if you look at the neural network as a whole, it's super easy. You just apply the chain rule, or you propagate the same way you did before, but from cell to cell. So for example, you start from this cell, right? It would be, as we saw before, the activation function that takes as inputs these hidden layer times the weights plus a bias for this node, right? And then this guy, you can rewrite it as well in function of these guys. So you'd start developing these y's into another term until you reach the inputs, which is called the forward propagation, basically. So you start from the input, the ending point is the input, and it's related to N1 via a very clear analytic expression. That's the beauty of feed-forward propagation. It's super analytic. You can see where it goes and etc. You can code it easily. And so the forward propagation gives you the function to evaluate the neural network output, but to make the neural network learn from data, you would use backward propagation. So for example, if you're trying to minimize a chi-squared, you're trying to basically find the derivative of this chi-squared with respect to the weights, because you're trying to find the minimum. So you want the derivative, you want to subtract the derivative. And this derivative would be related to the derivative of the neural network with respect to the weights. So usually in any minimization problem, you need the neural network's derivative with respect to its weights, these arrows. And there are many ways to do it. So you can do it numerically without caring about like you just take some approximation of the derivative via finite distance, right? or you can do it in an automatic differentiation or analytic. So both automatic and analytic gives you same accuracy on the derivation, but if you can code the analytic derivatives on a neural network, you can end up having a very performant minimization. It's the less time you would need to perform your minimization. So this is in blue versus automatic in red, and numerical in green, and this is time here. And this is where we increase the architecture of the neural network. So analytic always win. And this is basically, yeah, go ahead, Mathieu.
Okay, hello. Can you explain why we compute the derivative with respect to the weight and not the bias or other things?
It's also the bias. I didn't put it here, but you do both. So it's the set of all biases and weights that you need, precisely.
Okay.
It's just have a different, slightly different, I mean, no, actually, just you would replace here theta, and you get what you want. Yeah, thanks. So these are measured with this specific small example where we basically generated data across Legendre polynomial, and you can see that the neural network with even small architecture can approximate nicely the data. So with a random neural network, we just learn polynomial, Legendre polynomial of degree 10. And that feature is called universal approximation theorem. So neural networks can approximate any continuous function within a certain data range, which is one of the most important features of neural networks. All right, without diving in too much into details, hyper-optimization is where you try to find the best architecture of your neural network, the best activation function with respect to your problem at hand. And the only way to do it usually is that you don't have an educated guess. You just try. You try an architecture, for example, here, 3 inputs, 15 hidden layer neurons, and 6 outputs. You try 25, you try 15 and 20, you try 2 layers. And you try it many times. So you feed many options to your hyper-optimization algorithm. For example, here, the way you initiate the weights and biases, the learning rate you choose for your minimizer, and the activation function you use for a neural network. And the algorithm would take all of these options, make combinations, and test them. And eventually, it will give you the best option to use with respect to a certain figure of merit that you decide on. So for example, here, this architecture won because it has the most density and stability across chi-squared with respect to the others. This one won as well. This one won not only because, so it's not has density here, but you can see that it prefers this guy over ReLU, because ReLU has a possibility that it doesn't converge for a larger chi-square, etc. So it studies that for you and give you like, okay, use these settings, and this is what hyper-optimization does. In the next 3 minutes, I hope, I will just explain what the Monte-Carlo inference is, how to propagate uncertainty from the data into your neural network parameters. So starting from the Gaussian assumption, say you have a data and you have an uncertainty on the data, and this was estimated from a Gaussian distribution. So let's say you're measuring particle collisions and you're measuring one particle production, and the spectrum it gives of this particle production is just a Gaussian. So let's say you have a cross section, it has a specific, like all the production lies into a specific cross section, and it has a specific spread. This specific spread is translated into this covariance matrix, basically. And this mu is the experiment mean value, basically, the cross-section mean value. And xk is your observation, so every event where it hits, basically. And what you do in your fit, so usually experimentalists give you the mean value and the uncertainty, the covariance matrix. But in order to propagate the uncertainty to your model, you need to regenerate this xk yourself. So what you do is use this formula basically. So you use the covariance matrix to sample from the Gaussian distribution that the experimentalists gave you, and then you fit every xk independently. So you try to maximize the likelihood. So basically, the likelihood of finding the data with a set of parameters is that what you usually try to maximize to find the best parameters for your neural network. And instead of doing it once on the central value, you would do it n times on these sampled data. And that way you can have a sample of best parameters that their mean value is the best parameter, but their standard deviation reflects the data uncertainty. And finally, you can add also constraint into your minimization problem or your maximization. So maximizing the likelihood comes back, it's exactly the same as minimizing the chi-square that you all know, the figure of merit. So by adding an extra factor to your chi-squared, which is like takes the form of that, called Lagrange multiplier, you can constrain your neural network also to behave in a certain way. For example, you can implement here that your neural network should remain positive during the optimization. So you implement a function here that whenever the neural network gets negative, this contribution would become large. So the minimizer has to reduce it. And that's how the constraint is implemented. Finally, how to find this maximum likelihood or this minimum of chi-squared, you can use different algorithms. So you can explore the minimum via genetic algorithms that are just stochastic. So you just sample parameters randomly, not purely randomly, but following a genetic algorithm. Follows like the natural evolution, if you want. So if something works, you emphasize on it and you keep doing it. One of the minimizers that I'll be focusing on today is gradient descent algorithm. So basically, you start from a point in phase space, in the chi-squared phase space, and you start measuring derivatives. And you follow the derivative that leads you to the minimum. And that's what you can see here. These steps are basically subtraction of derivative, and you end up finding the minimum. These with different learning rates, so this is also important for the tutorial. You multiply the derivative with a certain constant, which is called the learning rate. So you try to, be careful about your steps. So you choose a small learning rate to go down slowly into the deepest direction, or you choose it to be larger, which could, make your minimizer find the solution faster, but you can also end up missing a certain solution. So this learning rate is very important for your efficiency. I won't go through trust region algorithms for the sake of time, but there's many other of these minimization methods. This one is just explores the minimum in circles, basically. It chooses a radius and it explores within this radius the solutions. One important thing is cross-validation that we spoke a bit about yesterday, is that usually with a neural network, it's easy to overfit. It's easy to learn, overlearn the data. So what you usually do is keep a specific subset of data outside the training, where you train on like 80%, let's say, of the data in blue, and you always check how well the neural network does against the validation set in red. So when you start, of course, these curves will go down together, because the more you go better on the training set, you'll do better on the validation. But at some point, these will converge, and then you start overfitting. And this is where the validation sets start to diverge, because you're overfitting over the training set. And this is what's called early stopping. So this is where you save this point as the best parameters of your fit. And this is cross-validation. All right, I'll let you dive into this tutorial, tutorial 1. do as much as you can. No worries about that. But just try to read and go through it one by one. The links are in the Slack channel, and if you can click here, you can find it as well. Raise your hand if you have any questions about the tutorial itself. And in the last 5 minutes, we will discuss what you guys found, basically. All right. I will. So this basically computes the learning rate from the previous step that you were able to find. And the way to do it is just copy the previous algorithm, but instead inject this learning rate. And then let's see what happens. So now NK is just, it's not an argument anymore, it's just computed every step. And if I load this guy, same thing, I just rerun with adaptive gradient descent. And you can see, starting from 2, it takes only 1 step to find the minimum in that case, as opposed to before. And usually in the proper, like when you solve proper problems, you would use always adaptive gradient descent. So you would not fix the learning rate yourself. You would give it for the algorithm to find it. And you save a lot of iterations, basically. If you have questions, I will stop here for the moment. Linear regression, so there's no machine learning, by the way, going on yet. I thought minimizers are the start to discuss machine learning. In the second hour, there won't be like exercises like that. There will be a complete tutorial, and you'll be using neural networks in the second one. But if you feel like it, just continue the notebook. And if you have any questions, you have 3 minutes. I'm staying here, so if you want, just let me know what you have questions.
One?
Yes, I was waiting to see if there was any raised hand.
Okay.
Let's give 2 more minutes.
Yeah, sure. I think I went a bit too fast. I should.
It's okay, because in principle, after the second lecture, there is an informal discussion, so maybe we can take some of that time to.
Okay, cool.
For questions on the tutorials, or.
Cool.
I mean, we're a bit
So
flexible.
we'll feel less shy, maybe. So.
Yeah.
Yeah. Right. I want to hear also how difficult people found to like first time to have a notebook and in 30 minutes to write something in Python. Like someone can tell me they found it easy, they found it difficult.
Come on, guys.
I thought it was fine, but I do lattice, so coding is my primary work.
Okay, all right. Thanks, Joseph.
Yeah, so I had a doubt.
Uh-huh.
Yeah, so at the end of this code, you show a graph of average cost versus number of iterations, right?
Yes. Yeah.
How are you calculating this cost? And I mean, why? I mean, I don't understand the dependence of this cost versus iterations.
All right. Let me reach the cell. Skipping a lot of steps. Okay. So the question is, how do I compute it, or why?
Yeah, so now as you increase the number of iterations, the cost decreases.
Yes. Yes, because your model gets closer to the description of the data. So the distance between your model and data decreases. So this is what the cost is.
So your cost is some kind of radius of convergence.
If you want, yes, it's defined. So if you look at how the cost is defined, let's look it up.
Yeah, it's that cosine of.
You can see here, right? So lambda, okay, h, which is theta plus theta x, okay, minus y. So what you're doing is that you're modeling, you have a model which is a linear model. So theta 0, theta 1 are your parameters. And this is your linear model. And you're trying to minimize the distance with the data, which is y indexed I, right? So you start with a random value, and this is why your cost would be very high because the distance would be large. But then you start applying the derivative, right? You start going to the minimum, and this distance would reduce more and more until you reach a plateau, basically, where you just, with the resolution of your data, you can't do better than that. And this is
right. So this is the radius of convergence, actually.
It depends on how you define it, but yes. I mean, you can call it here, for example, you can see that it converges around 2 iterations, right? Or
it's
right
2 million, right? Or is it just?
Yeah, 2 million. Yeah, of course. Yeah. And you can see, I mean, you can't get, at some point, you can't get the cost to 0 because you can't just go through these points with a linear model.
Yeah.
But in a case of a neural network, for example, a case of overfitting is just going through every point of these like that, right? Which is, you try to avoid usually. And we'll see that in the next tutorial, basically.
Right. So now here we decrease, let's say there is the experimental value, and then we get a theoretical value, and then we try to decrease the difference between them. And that's essentially the cost which you showed. Now, in realistic cases, we also have the case where the error comes in. And that plays a huge role, especially in chi-square. The error would be high or less would depend on whether how important that point is.
Very good. Very good. In the next, so let me see, this cost, I think, as you said, is not normalized by uncertainty. No, this is, this is called least square, right? There's no uncertainty here. In the next tutorial, we will use a chi-squared where we exactly weight the data with uncertainty. Very good.
Thank you.
Thank you.
Okay, so I would say that this is the last question for this first part of the session. Let's thank Rabah for the lecture with a virtual clap. And I would say that we can meet again in about 15 minutes. I would say it's 2:34 in my watch. Let's say at 2:50.